phase relationships between voltage and current. Now, if we were to plot my voltage on this axis and my current on this axis, and I have a fixed resistor, if I happen to have something like this, and I have a switch, and let's say that this is 10 ohms, and let's say this is 10 volts. And so if I'm looking for my I, V, I, and R, according to Ohm's law, if I'm looking for I, my I is calculated as V divided by R, correct? Everybody, so far so good? We started this on the first week. So if I have a 10 volt source and I have a 10 ohm resistor, I take 10 divided by 10. What is my current? My current would be right here, 10, and my current would be, let's say, at 1 ampere. 1 ampere. 1A. If I were to vary this, if I put a diagonal across this source, and that's kind of a bad drawing, I apologize. Let me redo this. This is your voltage source. If I put a diagonal across it in this fashion, that means this is a variable. So if this is a variable, what would happen if I take the volts down to 5 volts? Still 10 ohms. If I take it down to 5 volts, this would work out to be 0.5 amps. If I take it down to 1 volt, 1 divided by 10, this would work out to be 0.10 amps. So what you do here is you get the visualization right here. If I go to connect the dots, like this, if I go to connect the dots, this is a very linear relationship. What this goes to show is this: as I increase voltage, current increases proportionally. So if I start off with 1 volt with a 10 ohm resistor, I will have 0.1 amp. If I increase it to 5 volts, I will have half an amp. If I increase it all the way up to 10 volts, I will have 1 amp. So I get a very steady linear relationship between voltage and current when we're talking about this guy right here. And this guy is a resistor. So what can we conclude about the phase relationships between voltage and current with respect to a resistor? Hopefully we can make this conclusion. Conclusion. With respect to resistors, voltage and current are in phase, meaning they occur at the same rate. Now, that's DC. Now, suppose I change this to an AC circuit. If I go to change this to an AC circuit, another one here. Now I go to put in an AC source, circle here, and let's make this a like so, and then I have a switch like so, and I'm going to make this a variable AC source, and I'm going to say the AC source will go from 0 up to 10 volts peak. And let's say this is a 1 ohm resistor. So R is equal to 1 ohm. So what would happen if I were to increase, if I go to 1 volt across 1 ohm? What is my current if I have 1 volt across 1 ohm? And the question goes to Brad. If I have 1 volt source and I have a 1 ohm resistor and I'm looking for current, put my finger over the I, my current's equal to what's left. What do you see in my circle? V over R, right? So
Yes,
if the V is 1 volt and the R is 1 ohm, then what's my current?
1.
1 amp. Okay,
Yeah, 1
started
amp.
with 1 amp right there. Suppose I double my voltage. Suppose I go to 2 volts, but my ohms stay here. What is 2 volts over 1 ohm, Brad?
That's 2 amps.
2 amps, precisely, 2 amps. So if we continue with this, 3 volts will give us 3 amps, and then 4 volts would give us 4 amps, and I go to 5 volts, peak, these are all volts peak, this will give us 5 amps, and yes, these are all peak as well, eh? Let's start off with peak voltages. So if I go to plot this like so, and like so, I have, again, a what type of relationship? I have a linear relationship. And linear means straight line. So like we did earlier, we made a conclusion on the previous paper. The conclusion was with respect to resistors, voltage and current are in phase. Well, if I were to introduce, since this is an AC signal, and I were to introduce my V in this way, where this would reach a 10 volt peak here, this would reach a 10 volt, negative 10 volt peak over here, this would be at 0 volts. As I introduce this waveform to the circuit, how will my current look? Well, my current would be proportional. It would be like so and like so. Yes, it would be pretty much the same shape following the same waveform. So my current changes match voltage changes. They, meaning VR and IR, are in phase. Okay, the two waveforms are the same. So with resistors, this is what we see happens. However, with capacitors, something totally different happens. With capacitors, if you recall, we had a DC source, a switch, a resistors in the circuit, and then there would be a capacitor. And we know through previous discussions, the moment we close that switch, if this was a 10 volt DC source, and this is a 1 ohm resistor, and then the capacitor is whatever the capacitor is, let's say the capacitor is equal to 2 microfarads. This capacitor, the moment we close the switch, doesn't charge up to the 10 volts immediately. It takes a period of time for this to charge up to 10. So we had a discussion on something called time constants. And how many time constants does it take for a capacitor to reach full charge? Brad, do you remember? How many time constants for a cap to reach full charge?
I don't actually remember.
No, Robert, actually I meant to ask Robert because Brad had the last 2 questions. So
Takes 5.
It's 5 time constants. So we have, and the symbol for time constant, the word is tau, T-A-U, and the symbol looks like a cursive T, or like the letter pi without the 2 sticks coming down. And this is time constant. time constant, and it takes 1, 2, 3, 4, 5. So 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. It takes a while for this thing to reach full charge. In each time constant from 0, this capacitor will charge roughly 63.2%. And so one point it'll be here, another 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 point it'll be here. And so your voltage on a capacitor builds up in this fashion. So this would be your VC. The VC takes 5 time constants for us to reach full charge. Now, I won't go through the math of each of these time constant exercises again. We've done that previously. What happens with respect to current? The moment we close that switch, current is at maximum. Your IC is equal to maximum right at the moment we close the switch. But over each time constant, that current will diminish, 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 diminish. And so the current will come down with this type of a curve, okay? So we don't have the same type of phase relationship that we did here with resistors. We have something that is out of phase. Which one of these is at maximum first? 0 being the beginning, 5 tau being the end. Which one's at maximum at the beginning? Current is at maximum. Then what happens at the end of 5 tau? Then voltage goes to maximum. So current starts off as maximum, and then current goes to 0 amps. Voltage starts off equals 0 volts, but it goes to maximum. So we have this, we can make this statement for RC circuits. What does RC stand for, Jacqueline? What does RC stand for?
Resistance times capacitance.
Yeah, we have resistance times resistance capacitance circuits. So in circuits where we have a resistor and a capacitor, we have this very interesting relationship. So for RC circuits, we can say current I, which is equal to current, leads V by 90 degrees. We can also say V, which is equal to voltage, lags current by 90 degrees. Current comes first, voltage comes after. And because we have this unique relationship, we have a memory tool. And memory tools are known by mnemonics. And the mnemonic I want to remind you of, I've given this to you once before, is ELi the ICE Man. ELi the ICE Man. And here for ELi the ICE Man, this is a really nice memory tool that helps you keep straight which one of these comes first. And so because we're dealing with a capacitor, C stands for capacitance and R is for resistance. So there's the RC for the RC circuit. Because we're dealing with a capacitor, ICE comes into play. The C stands for caps. And which letters do I have on either side of the middle letter C? I happen to have I on the side, and I happen to have E on this side. If you recall, when we showed you Ohm's law circles before, and the Ohm's law circles were drawn previously as VIR, we said that in many textbooks, instead of V, they use E, EIR, okay? So E is the same as V, for electromotive force. They are interchangeable, and many textbooks go by EIR. We've been using VIR. They mean the same thing. So in this mnemonic, ELi the ICE Man, this stands for current. This stands for voltage. And if you look at this carefully, which letter is in front of the C, which letter is after the C? The I is in front of the C, yes? And the I stands for what? Current. It comes first. It leads, okay? The E comes last. It lags. Does the memory tool ICE correspond with, does this correspond with our statement here that current leads voltage or voltage lags current? Current comes first, it leads. Voltage comes last, it lags. And if we look at the time constant chart, we can see current happens first before voltage happens next. Now, why is this significant to us in today's discussion? In today's discussion, I'm going to talk about AC circuits in particular. So with AC circuits, we have this interesting phenomenon. We have an R, we have a C, and I'll close this with a switch. And so this guy, just like the DC circuits, will behave according to this graph. Current will happen first before voltage reaches maximum. So what happens here is different than what happens with a resistor. Perhaps I should have started with a resistor. So here's a resistor, here's a switch, and AC source. So what happens the moment I close this switch, we've already determined that your V and your I, they work proportionally and linearly with each other. They are said to be in phase. So I would draw my arrow here. This would represent my VR, and this would represent my IR. And because they're both pointing at the same direction, they are said to be in phase. With respect to a capacitor and a resistor, with AC, we don't have this phenomenon occur. With respect to a capacitor with AC, which one comes first? According to ELi the ICE Man, capacitor says, what comes first? What's it say over here, Yusuf?
Current.
Current comes first before E, and E stands for what, Yusuf?
Electromotive force, voltage.
Voltage, precisely. And so the way that we would draw this is here. I would have this guy happen first. I would have my IC happen first before my VC happens next. And they differ from each other by 90 degrees. And the way that we reconcile our degrees, this would be a starting point, this is a starting point, and we would be rotating around something called a unit circle. So here's the center, and we would have 4 axes, and this would be marked 0 degrees. This would be moving up in this direction. This would be 90 degrees. Moving another here, this would be 180 degrees. Moving further down here, this would be 270 degrees. And moving back over here all the way around, this side is known as 360 degrees. So if you move in a circular fashion, right here, imagine this is a circle. How many degrees are there in a circle? There happens to be you may recall back in middle school and high school geometry, there's 360 degrees in a circle. How do they measure that? They always measure this pointing at 3 o'clock, and this would be 3 o'clock. Imagine, if you will, you have the face of a clock. So this is 3 o'clock, 12 o'clock, 9 o'clock, 6 o'clock. Got that? 3 o'clock, 12 o'clock, 9 o'clock, 6 o'clock. Well, at 3 o'clock is where we start counting our degrees, 0 degrees. And if we rotate up to 12 o'clock, we will have moved how many degrees of a circle? 90 degrees. And if we move all the way over to 9 o'clock, we will have moved from the beginning a full 90 plus 90, or 180 degrees. And all the way back over to here gives us 360. Let me ask you a question. Jacqueline, I have a question for you. If I move in a counterclockwise fashion from here, rotating up to 12 o'clock, and I call this 90 degrees, what would happen if I rotate in the reverse direction from 0 and I come down to 6 o'clock? Is there an alternative designation for my 6 o'clock position in terms of degrees?
Did you call it negative 90 degrees?
We would call this negative 90 degrees, precisely. So at 12 o'clock, we have positive 90 degrees, and at 6 o'clock, we have negative 90 degrees. So in other classes, in your math classes, your geometry and physics classes, they would be concerned about 360 degrees. For us, in electronics, we're really only interested in this half of our circle. We're only interested in 0 to positive 90 or 0 to negative 90. That's all we're interested in for electronics. And if we take a look up here, you can see that we have this upper right-hand quadrant of our circle where the IC is 90 degrees leading the VC. And let me show it to you using different color pens. So if I may, I'm going to raise this up so we can see this a little better. Quick focus. Okay. So I'm going to have this guy, this pen will represent, this will be a, let me define something for you. Vector equals an arrow of a specific length pointing in a specific direction. Okay? A vector is an arrow of a specific length pointing in a very specific direction. We have something called phasors, which are vectors. They're fundamentally the same thing, except phasors, these are equal to vectors used in, let's say, for us, electronics. So if I were to take this and I were to go in this direction and say IC is equal to 4 milliamps peak, have I drawn a vector? Yes, I've drawn a vector. Does this vector have a specific length? Yes. Is this vector pointing at a specific direction? Yes. A phasor is the same thing. It is a vector, but we're using this in electronics. So it is 4 amperes. From here to here is 4 amps, 4 milliamps peak. And what is my direction? If I'm pointing in this direction, 3 o'clock on my unit circle is how many degrees? Wei Ji, how many degrees is my 3 o'clock position? How many degrees is my
0 degrees.
3 o'clock position? My 3 o'clock position is 0 degrees. So this is 3 milliamps, comma, 0 degrees. So this phasor, all phasors, vectors, they have to have two things. They have to have They must have a magnitude, losing ink. They must have a magnitude, and they must have a direction. So they must have a magnitude and a direction. So the magnitude is your specific length, and the direction is pointing in a specific direction. So what is my magnitude for this phasor? My magnitude for this phasor is 4 milliamp peak. What is my direction? 90 degrees. Now, because current happens before voltage on the same circuit, this will start following the sine wave, and then it will reach a point where voltage will appear. So these guys will rotate in this fashion, rotate in this fashion like so. And so by the time voltage appears at maximum, what has happened to the current vector? The current phasor has already moved up 90 degrees. So this is kind of how it looks. It starts off here, your current's at maximum at the start point. And then this will rotate, 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 rotate. And these two vectors are 90 degrees apart. IC and DC. So by the time this appears, that's already at 90 degrees ahead of it. So with respect to your, and let me draw this guy here. This is my VC. This would be at negative 90 degrees. And then I'm going to rotate right here. This is my IC. And here is my VC. And I'm still rotating in this fashion. And if I continue rotating, then this guy will be pointing, IC will be pointing straight up, and my VC will be pointing in this direction, like so. And so there is a 90-degree difference between these two phasors, 90 degrees right there. And which one came first as this drawing is rotating? This was first, and this was last, okay? So there is a very, very unique and very specific phase difference with respect to our quantities with electronics. We're going to be able to see this using an O-scope. We're going to be able to do all the measurements in just a moment. So having said that, let me point our attention to this document. So hopefully by now you will have downloaded this, and if you haven't printed it out, it's okay. We can have this one here that we can work with. All right, so the gist of this exercise is to see what happens numerically, calculation-wise, the angles, and we're also going to do this using, we're also going to check the circuit out using MultisimLIVE. So you are introduced to an AC signal. The AC signal has a volts peak, a 15 volts peak, has frequency 5.1 kilohertz. It has a capacitor value that's given as #233. We have to decode that. Then you have a resistor that's given with a color code, violet, blue, brown, gold, at maximum tolerance. So you're going to have to do some decoding of certain things. So how did we decode the capacitor? Remember how to decode the capacitor. With decoding capacitors, so just as a review, decoding cap value of, in this case, what, 233? 233, so #233. If we were decoding this capacitor value, as long as you follow the rules, the decoding is pretty easy. So what were the rules? The rules were, first value equals first digit. The second value equals second digit. The third value is equal to what? Brad? And you may have missed this. I don't recall if you got
Its number is zeros, right?
number of zeros. Right. Excellent. So number of zeros. And we have to follow that, followed with, or followed by, and Weiji, do you remember what we have to follow this by?
Picofarad.
We have to follow this by picofarads, okay? PF, picofarads. Now, we have to decode this guy. So my first value is a 2, so I'm going to write down, so a number 233 is equal to a 2. My second value is my second digit, so my second digit is a 3. My third value is number of zeros, so how many zeros am I going to write down? 3 zeros. 1, 2, 3. And then I have to follow it with picofarads. Not milliamps, not microvolts, not kilo ohms, but picofarads. Very specific. If you go to key this value into your calculator, let's go ahead and do that, 23,000. How do I key in picofarads? You have to have your little handy card to look it up if you don't remember, but that would be exponent. So I would hit the EXP, I would hit the EXP key right there, and exponent change sign. So I would hit the change sign key right there. So now the display shows me 23000 with a exponent negative. And what power of 10 is a pico? Negative what? Jacqueline?
12.
Negative 12. Good. So that's what I do. I just punch in the 2, the 3, the 3 zeros, exponent negative 12, and let the calculator do the work for me because I have a button here marked ENG, don't I? So the moment I hit ENG, voila. Oh, I have to hit equals first, silly guy. Equals, and then ENG. And so in doing so, what's the calculator show me? It shows me 23 power negative 9. So what is that?
Nano.
How do I speak it?
Nano.
Yeah, nano. So this would be 23 nanofarads. And who told us so? Your calculator told you so, 23 nanofarads, which in another discussion we said that we really don't, nano is not a standard value. Separately, you would decode that to be 0.023 microfarads. But I'll leave that off the discussion for now. I'm happy if you got the 23 nanofarads. And for the sake of this exercise, we will just simply write down capacitor value 233 is 23 nanofarads. I will write down the other answer, which is 0.023 microfarads. Don't worry about that conversion for this exercise. So solutions. All right, so are we okay with that review of how to decode a capacitor value? So decoding a capacitor value, as long as you follow the rules, first value, first digit, second value, second digit, third value, number of zeros followed by picofarad. So 233 is a 23 followed by 3 zeros, followed by PF. Punch this into your calculator, you get 23 nanofarads, which is good enough for us to fill into this part of our answer blank. Now, what's our next quantity? The next quantity is X sub C. What is X sub C? Well, if you recall, your X sub C, because this is a subscript and we pronounce this as X sub C. I'll write it out. X sub C is how we speak it. And this stands for what? Capacitive reactance. Capacitive reactance. What is capacitive reactance? Doesn't this sound similar to resistance? Because this is also measured in ohms. So let me do a quick review here. resistance. What was the definition for resistance? Opposition to current by a resistor. Only a resistor has resistance. Resistors have resistance. And what type of current? Well, that current could be DC, that current could also be AC. It doesn't matter. Whether it's DC or AC, the opposition to current demonstrated by a resistor is called resistance. So what is this thing here called? Reactance. Reactance is opposition to current by a cap or coil to AC. And it is measured in ohms. Okay, measured in ohms. So reactance, although it sounds similar to resistance, is not the same. However, the behavior is the same in that it is opposition to current. Opposition to current by a what's it say here? By a cap or a coil. So we have two different kinds of reactance. We have X sub C, which is your capacitive reactance. And then we also have X sub L, which is inductive reactance. I'll save that conversation for another time, but let's stay with X sub C. There's a formula for us to calculate X sub C. 1 over 2 pi FC. There's your formula for capacitive reactance. 1 over 2 pi FC. So whenever you have a 1 over anything, does this look similar to our reciprocal calculations that we've done before? You're not afraid of 1 over any quantity, because what do we do to solve? We solve the denominator first, equals some value, and then you hit your reciprocal key. Once you calculate the denominator, you hit your wonderful x -1 button, and then equal in order to get your result. So let's see how this plays out in your calculator for this particular capacitor of 23 nanofarads. It would work out this way. 2 times, and you're going to have to find your pi key. So on this particular calculator, it is a second function or a shift function, yeah? You have a shift, and the pi is right above the EXP key. So we would do 2 times shift your pi key. So 2 times, let me clear, turn it on, that would help. So 2 times shift pi. Does the calculator actually show us the pi symbol? Then it shows us 2 times pi. Then we're going to multiply this by our frequency, and our frequency in this case was given as what? 5.1 kilo. So I'm going to put in 5.1 EXP, and kilo is what power of 10? 3. So I will do times 5.1 exponent 3. So far so good, but I have one more thing to multiply. I have to multiply by what? There's a C here, right? I already did the 2, the times, the pi, times the F. Now I have to multiply by the C. So I'll multiply by, and my C value we determined earlier was 23 nanofarads. So 23 EXP, nano brings us to the negative side, and nano is what power of 10? 9. So now have I keyed in everything in my denominator, 2 times pi times frequency times capacitance. So 2 times shift pi to get my pi key times 5.1 exponent 3 times 23 exponent -9. So what do I need to do here at this point? I have to hit equals. So let me multiply this by 23 exponent -9, and I will hit equals. So I get this really odd looking number, 10 -4. What did I just calculate, my friends? Is that my reactance? No. What I just calculated was the stuff underneath the 1 divide by. How do I divide this back into 1? There's a magic key called your reciprocal key, which is this guy right there, reciprocal key. It is your, after you hit equals, you hit your x negative 1, and then hit equals again. So I will hit the x negative 1 key right now, and hit equals again. And guess what? Does your calculator match mine for this answer? What is your calculated answer, Yusuf?
That was it. 1.36 kilo.
And reactance is measured in ohms, okay? So we would speak it as ohms, and that's what your calculator should show. My calculator here shows what you would round off to be 1.36 and 10 power of 3. So everybody able to confirm that calculation? Give me a thumbs up. If you're not, just follow that keystroke sequence again, and you should be able to get it. So if we can concur that this is your ohms that's demonstrated by your capacitor, we can write that guy in. 1.36 kilo ohms. So we now have two pieces of the puzzle. We now have the capacitor value, which we needed to calculate capacitive reactance. We can write capacitive reactance right here, 1.36 kilo ohms. We now need an R value. Wow, well, guess what? Code didn't give you a straight ohmic value. You were asked to think and prepare yourself for the final exam coming up over a month from now, still plenty of time. But let's go ahead and drill our resistor color coding. Violet, blue, brown, gold. Violet, blue, brown, gold. So Jacqueline, how do you interpret, oh, this is at maximum tolerance also. So how do we decode a violet, blue, brown, gold? This is a 4-band resistor. So we have violet, blue, brown, gold at max. So Jacqueline, help us out. First color band is violet. What does it represent to us?
It represents the first digit.
Okay, that's my first digit. And my first digit happens to be what value?
I do not have my card with me. Let me get it.
Okay. And while she's getting her card, we want to remember that the second band would represent the second digit. Okay, so the first band represents the first digit, second band represents the second digit, and the third band represents something, and the fourth band represents something. So this is good review for us, for sure. Now, let's...
So, Mr. Koh.
My dear, okay. So the first band, first digit, and the first digit violet represents what numeric value?
7.
A 7. Excellent. All right. We stated that the second band represents the second digit, which is blue. And so blue is represented by what value, Jacqueline?
6.
Okay, that would give us a 6. So far, so good. And the third band represents, does it represent a third digit in this particular case?
No, it is number of zeros.
Okay, this represents number of zeros. And how many zeros does brown represent?
We get 1 0.
We get 1 0. Now keep in mind, brown represents 1. We do not write a 1 here. We write the number of zeros. Brown represents 1 0. There it is. Okay? And gold represents what, the fourth band represents what information? It's called what?
Tolerance.
Tolerance. Tolerance. And tolerance is your degree of error, margin of error. Degree of error. And gold represents what percentage of error is possible with this.
Plus or minus
Jacqueline?
5%.
Plus or minus 5%. Very good. So we have now completed something known as a coded value. We have the coded value. We did this since week 1. Now, the question is, how do I reconcile this at maximum tolerance? Because this can go as low as minus 5% or it can go as high as plus 5%. How do I calculate this at plus 5%? Question goes to Yusuf. How do I do this?
You want to know how to calculate the tolerance?
I want to calculate what the value will be at maximum tolerance.
It'll be 760 times 1.05.
So 760, and we're going to multiply this by a decimal factor of 1.05. And that should be in your notes, all the different decimal factors that we have for calculating maximums and minimums for the different percentages of tolerance. I won't take time to review that now. That's in your notes. So we're going to take 760 times 1.05. And Yusuf, that calculates to be a whopping how many ohms?
798 ohms.
798 ohms. Is everybody okay with how we decoded that resistor value? You will not be given a straight number of ohms. You will not be given a straight number of capacitors. You will be asked to decode a capacitor number. You will be asked to decode a resistor color band at maximum or minimum tolerance. So be informed that those are elements that will be part of tests moving forward. So we just decoded violet, blue, brown, gold at maximum 798 ohms. We will write that in here, 798 ohms, and write that in here, 798 ohms. Woo-hoo. Very nice. So far, so good. Now, we use these phasors. R is a phasor of what length? 798 ohms. What is the angle at which this is moving? This is at 0 degrees. X sub C is another phasor of 1.36 kilo ohms. What is its angle? If it's pointing down, what is its angle if it's pointing down relative to the R phasor? Wei-Ji?
270
Or?
degree, negative 90.
Yes, we would call that as negative 90 degrees, okay? So anything, so imagine here, watch my pen, anything moving in this direction from horizontal, anything moving in this counterclockwise direction from 0 would be a positive degree. Anything moving in this direction from 0 would be a negative degree, all right? Moving in this direction would be positive degrees. Moving in this direction is negative degrees. And so if you take a look at what we're solving for, we have to solve for the hypotenuse of this right triangle, because this is total ohms. You have ohms by the resistor, you have ohms by the capacitor, but these guys are out of phase with each other. How do you find the total ohms in the circuit? You can't add them up, because this is not resistance. You can't add that up because that's not just capacitive reactance. So the way we do this, and the reason why we've practiced our Pythagorean theorem, and the reason why we've practiced our SOH CAH TOA exercises, was specifically in preparation for this. So we're going to do some Pythagorean theorem here, right? Because the hypotenuse, remember, C A squared plus B squared equals C squared, yes? Or C squared is equal to A squared plus B squared, or C is equal to the square root of A squared plus B squared. All of those you had in your notes from before. How do I reconcile this hypotenuse? Is this this is side C of a triangle. Your impedance would be calculated as the square root of this number squared and this number squared. So your impedance would work out this way. And I'll just go ahead and get another piece of paper. Take us just a moment here. Okay. Our impedance Z And to scale, the drawing actually should look something closer to this, because your X sub C equals 1.36 kilo ohms at negative 90 degrees. Your R phasor, R is equal to 798 ohms at 0 degrees. And so I'm making the length of the phasors more proportional to their values. Shouldn't 1.36 kilo, 1,360 ohms be longer phasor than 798? It should be. So clearly this drawing is not to scale, but the math will be in a moment. But this one is to scale as much as I can do. And so we need to calculate this in this this side of the triangle. And so we will do this math-wise this way. So Z is equal to the square root of 798 squared plus 1.36K squared. Now, on the surface, that might look pretty intimidating. It's actually not so intimidating because you've got a great $8.98 calculator with its own square root key. It's really cool. So all you have to do this exercise is this. You would hit square root key and turn this on, get the square root key. Now, in your calculator, it doesn't generate an open parentheses. I highly encourage you to put in open parentheses. Open parentheses. Then we will take 798, and what are we going to do? We're going to use the x squared key, which is right here. You have an x squared key, so I'm going to square it. And then I'm going to add it to, right, 798 squared. I'm going to add it to what? 1.36 kilo, so 1.36 exponent 3. That's my kilo. And what do I have to do with it? I have to square it. And after I square it, then I should close parentheses and then hit equals. So that should be my keystroke sequence in order to calculate this side of the triangle, Z. And so if I do this with my calculator, I'm going to square root right there, and I have an open parentheses right there. I'm going to do 798, and then I'm going to hit my square key there so you can see it squared. And now I'm going to hit plus. So here's my plus key so you can see plus. And then 1.36 exponent. Kilo is a 3. What do I have to do after I enter kilo? I have to square it. So I better hit my square key. It's squared. And then followed by close parentheses, close, and then end it with equal sign, equals. And what is it that you all should calculate? Don't sit there watching me. You should be doing this calculation as I was doing the calculation. This is not a watch and be fascinated. This is a watch and do show. So if you'd done it, you would round this off to be 1.58 kilo ohms, yes? So the Z works out to be 1.58 kilo ohms. So what is this thing called Z? Hadn't seen that one before. Well, if you recall your engineering, your electrical terms, Z is a new word called impedance. Impedance. I-M-P-E-D-A-N-C-E, impedance. And if you look it up on your electrical terms handout, you'll recall that impedance is equal to the total ohms in an AC circuit. Total ohms, period. That's it, the total ohms. It is a combination of, this is equal to combination of R is one component, X sub C is another component, and this next week we'll introduce you to X sub L. So any combination of those total ohms will be called impedance. And in this drawing, let me recap for you. R stands for resistance. Right there. R stands for resistance. X sub C stands for capacitive reactance. Z stands for impedance. So all the triangles you've been playing with for the past week and a half now are very pertinent when they come down to analyzing what's going on in an electrical circuit. These numbers follow all the same rules of math that you've been playing with for Pythagorean theorem and SOH CAH TOA. We'll get to SOH CAH TOA in a moment, but certainly for Pythagorean theorem, calculating the hypotenuse of a right triangle, boom, it's right there. You've done this, and we've just done it again. But keep in mind, the R phasor, the resistance phasor, is always pointing at how many degrees? 0 degrees. And we call this phasor what? Resistance. We have another phasor, in this case, pointing down. X sub C points down. When it points down, it is how many degrees? Negative 90 degrees. What do we call the X sub C phasor? It is called capacitive reactance. And they form these sides of a right triangle. So if I go from the starting point and connect it to the end point, I draw this line. This line is the hypotenuse of a right triangle. This, in electrical terms, represents something we call impedance. And impedance is represented by the symbol Z, and is measured in units of ohms. How do I calculate it? Pythagorean theorem. Now do I have a value of Z? So I'm going to put that value of Z right here. Total ohms is 1.58 kilo ohms. I'm going to write it there, and 1.58 kilo ohms right over here, okay? One more thing to calculate in this first group of calculations is current. That's a voltage source. We're going to have currents moving in here, moving around this. How do I find current? Well, Ohm's law, new circle, you learned it this way. Ohm's law was learned VIR. Well, we're now going to expand it this way, VI omega, because this omega can be R, this omega can be an X sub C, this omega can be X sub L, which we'll talk more about next week. This can also represent Z. So there's 4 quantities here that are all measured with the omega, according to Ohm's law. So if I want current in this AC circuit, what do? I cover up the I with my finger, and it's going to be V divided by ohms, yes? That's how we've been using Ohm's law since the first week. So which voltage by which ohms? Well, in this particular circuit, we have a 15-volt peak, but we have 3 different ohms. We have ohms for X sub C, you have ohms for R, you have ohms for Z. Which one of these numbers am I going to use to find total current? What do you think we're going to do, Wei Ji?
We divide it by the impedance.
We should divide total voltage by total ohms, because we said, you're right, the impedance represents total ohms. So if I want total current, I have to use total ohms. So in this particular case, my IT is going to be equal to 15 volts peak divided by my 1.58 kilo ohms. So let's go ahead and do that. Here's this, take my 15 volt peak and divide by 1.58. exponent, hit my exponent key. Kilo is 3. And now before I hit equals, what number do you calculate on your calculator? Robert, what do you have? 15 divided by 1.58 kilo gives you what?
I got 9.49 milliamps.
And we should all be able to concur Robert's calculations, as my calculator does also. 9.49 milliamps. Everybody good with that? 9.49 milliamps peak. Because that was a volts peak, we have to have milliamps peak. So far, so good? All right. Just a few more calculations on this. And so in our circuit, we happen to have, and I'm just gonna, we have so many markings on the original. Just gonna draw a clean version. We have a capacitor here, we have a resistor here. Close this up. This represents 798 ohms. This represents 1.36 kilo ohms. This is a 15 volt peak. So this represents R, and this represents X sub C. Z is total ohms. And Z was calculated as 1.5, what did we say, 59? 1.58 kilo ohms. So what we're asked to think about right now is current. And remember, AC moves in both directions. Part of the time is clockwise, part of the time is counterclockwise. So your IT is equal to your V total over your ohms total. In this case was 15 volt peak, divide by 1.58 kilo ohms. So your current worked out to be 9.49 milliamps peak. We just did this, 9.49 milliamps peak. So what I'm going to ask you to think about next is what kind of voltage are we going to be able to see if we used a meter and tried to measure the voltage across the capacitor and voltage across the resistor? What are we going to be able to see? How would we calculate VC? How would we calculate VR? VR is across the resistor. VC would be across the capacitor. How would we go about doing this? Well, same way we've done Ohm's law past 20 minutes. So if you recall, V, I, ohms, yes? So if I want a V, what do? Cover up the V, and so what do I have? I times ohms, yes? Do I have an I moving in the circuit of 9.49 milliamps, class? Yep. This is the current flowing in the circuit.
Yep.
Do I have ohms for each of these components? I have ohms for the X sub C, and I have ohms for this guy. Sure do. So I should be able to do this way. My VC should be equal to I total times X sub C. Should be equal to 9.49 milliamps peak, and multiply this by 1.36 kilo ohms. So what does my VC calculate to be? Let's go ahead and do that. 9.49, I'll clear, I'll just use the same rounded numbers as you all. 9.49, and I will do exponent -3, so there's my 9.49 milli, and I'm going to multiply this by 1.36 exponent 3 for my 1.36 kilo, and the answer calculates to be what, Yusuf?
12.91 volts.
Engineering, and yes, I would concur. We have a 12.91 volts peak, yes? The next quantity we want to calculate is the voltage across the resistor. So VR is equal to IT times R. And so we happen to have 9.49 milliamps peak, we're going to multiply it by 798 ohms. And we'll go ahead and do this together. And clear. So on the calculator, I would have 9.49 exponent -3. So there's my 9.49 milli. And I'm going to multiply this by 798 right there. And when I hit equals, Yusuf, what number do we calculate for voltage across the resistor?
7.57 volts.
Okay, and I concur with my calculator, 7.57 volts it is. So VR equals 7.57 volts peak. Is everybody okay with calculating these last two voltages? We just now calculated the voltage on the capacitor and the voltage across my resistor. This guy worked out to be, so VC worked out to be 12.91 volts peak, and VR worked out to be 7.57 volt peak. Those are nice numbers. How do we know they're right? Is there a way to double check to see if they're right or wrong?
They should add up to
Kirchhoff says in any closed loop, these voltages should add up to the voltage source, yes? This plus this better add up to this. Well, if you look at this, you say, well, wait a minute. Come on, Co. 12.91, add 7.57. There's no way that's going to equal the 15. Did we do something wrong? Nope, we didn't do anything wrong. Let me show you very quickly how you can double check your math very easily. We have our VR, which we calculated as 7.57 volts peak. We have our VC, which we just calculated as 12.91 volts peak. Just like the other phasors, the ohm phasors were out of phase with each other, so are our voltage phasors. These are out of phase with each other. So if we wanted to add these, we can't just add the numbers together. We have to use Pythagorean theorem. My VT is here. So if I use Pythagorean theorem, hopefully they will add up to be my 15 volt source, which is what we started with our circuit to begin with. Right there is a 15 volt source. Let's go ahead and see if that works out using Pythagorean theorem. So VT is equal to square root 0.57 volt peak squared plus 12.91 volt peak squared. And so on your keystroke sequence, it should be square root, open parentheses, 7.57, hit your square key, plus. Then 12.91, hit your square key, then hit close parentheses, then hit equals. If we follow that keystroke sequence, let's see what happens. Clear. Right here, square root, open parentheses, 7.57, and I'm going to square it, so x squared right there. Hit plus, here's my plus, there's my plus. Next one is 12.91, and what I'm going to do, I'm going to square it, so I'm going to hit my square key, then followed by close parentheses, there's my close parentheses, then followed by equals. Boom, enter. Do I end up with something really, really close to 15 volts? 14.97. Why is it not exactly 15? The reason why it's not exactly 15 is because we used rounded answers here. So this is pretty good. 14.97 volts peak. That's almost 15 volt peak. That way, this will give you the assurance this is done right. So we can now enter these numbers onto our answer sheet as well. So our VR peak was 7.57 volt peak. VC was 12.91 volt peak. And now phase angle. Phase angle, that's why you've been doing SOH CAH TOA. We need to find out how far this comes down. So for SOH CAH TOA, phase angle, let's go ahead and use this side. This was the last calculation. Let's go ahead and use our earliest calculations. This one and this one. These are earliest calculations. If this is theta, this side of the triangle has a name. What do I call this side of the triangle with respect to SOH CAH TOA? Question goes to Jacqueline.
Adjacent.
So this would be adjacent, ADJ. This side over here, with the 12.91, is called what side of the triangle, Jacqueline?
Opposite.
This would be opposite, because this one, which we're not using in this calculation, is your hypotenuse. But we're going to use these two because these are our earliest calculations. The letter adjacent starts with, the word adjacent starts with what letter? A. Yes, everybody? And opposite starts with what letter? Oh, you have an A and an O. Huh. So do we use so? Do we use CAH? Or do we use TOA? Which of these three has the A and the O? It turns out TOA is the one that has the A and the O. And if you remember from our notes before, TOA means this, that the tangent of an angle theta is equal to O over A. O is opposite over A, which is adjacent. So just looking at the letters TOA, we happen to have right here a T for tangent, we have an O for opposite in the numerator, and we have A for adjacent in the denominator. So using the mnemonic SOH CAH TOA helps you very, very quickly to be able to determine which function we're going to use. So tangent of angle theta is equal to opposite, which is 12.91 over adjacent, which is 7.57. Now, are we truly interested in the tangent of an angle, or do we just want the angle? We just want the angle. So if you recall, how do I move the tangent to the other side of the equation? I want to be left with angle theta. That's all I want to be left with on the left side of the equal sign. How do I move tangent to the other side? It's a simple manipulation called inverse tangent, tan -1. Is there a tan key on your calculator? Yeah. Is there an inverse tan right above it? Tan -1. How do I access tan -1? Isn't that a shift tan? So that's what we're going to do here. We're moving tan to the other side of the equation. So angle theta is equal to shift tan of 12.91 over 7.57. And on your calculator, you're going to do this. You're going to do shift tan. And I'm going to do that as well. So clear. So shift tan. Now, what it doesn't do is it doesn't give us an open parentheses. I need open parentheses. Open my parentheses right there. So open parentheses. And what am I shift tan? I'm going to do a 12.91. So 12.91 divide by 7.57 and close parentheses and then equals. So I will do 12.91 divide by 7.57, close parentheses, and now hit equals. And I will hit engineering, And how many degrees does this show me? 59.61 degrees. So we're almost there. We just calculated 59.61 because this is going down from 0 degrees, because this is going down. Technically, this should be a negative 59.61 degrees, okay? Now, the next part of this, I'm going to show you in Multisim. So I'm going to write this down, negative 59.61 degrees. That completes the calculation side of our work. The next side of our work is going to be in Multisim. In Multisim, we're going to verify all of this using Multisim. So I'm going to go change my view from the camera. I will now log in. I will continue to log in. I will create a circuit. I will it's awesome. Well, it's nice. It's nice that it's awesome. Okay, come on, give me my components. Be nice. Schematic. Okay, there is developing all my components. So I need an AC source, which I'm going to put right there. And I'm going to make this a little bigger so we can see things better. Okay, now we can see things a whole lot better. Like so. All right, and I'm going to need a capacitor. So come down here, find me a capacitor, and the capacitor will go here. And I'm going to go and grab me a resistor and put the resistor here. Now I need to rotate it, so I hit this little guy, it rotates. I'm going to punch in the value, so double click this guy, and my ohms comes up, so I'm going to punch in 798. Everybody see I'm punching in the number there, so I double clicked it. The document, the dialog box comes up. I get 700, and I get the enter value. I entered 798. Hit enter. So now my 798 space and enter. Okay, that gives me a cleaner looking. If you hit the space bar, it separates the omega symbol from the 798. So it's a little cleaner looking. The capacitor value, double click this guy, and it starts off as 1 micro. We wanted 23 nano, yes? So 23 space N for nano, right there, hit enter. So now do I have 23 nanofarads and a 798 ohms? I select the voltage source, so click on it. The voltage source will be 15 volts. And it specifies I can do peak voltage or RMS voltage. I'm going to leave this as peak voltage. So I have 15 here. And my frequency was 5.1 kilo. So I'm going to type in 5.1 space, type in the letter K, 5.1 kilo in my dialog box. Enter. Do I now have 15 volts peak? 5.1 kilo. Circuit's pretty easy to build, yeah? Connect here to here. Notice that this wire has a number 1 up here. The number is distracting. So on the dialog box on the right-hand side, select display. You see this checkbox for net labels? I'm going to uncheck this and watch the number 1 over this wire disappear. It really is distracting, so I'm going to uncheck it, and the 1 disappears, which is wonderful. I'm going to now connect this guy to here and uncheck to get rid of the 2. I do need a ground, so I'm going to connect a ground. Drag a ground. Hello, drag a ground to here. Nice. Okay, I'm going to connect from here to ground. And get rid of the net label. And one more connection from this side of the source to ground. So now I have a circuit that looks a lot like your schematic, yeah? I do need voltage probes, so I'm going to come up here, click voltage probe, voltage, and I'm going to put one right across my source, PR1 for my probe number 1. Click another one, I want a voltage probe, and I want this one over the resistor. So this is now probe number 2. So does this look remarkably like our circuit on our paper? So far, so good, yeah? Now, here's the magic. We will be able to put this, and let me, since we've drawn it so nicely, I'm gonna, downsize it a little because I need my screen space in order for me to demonstrate the waveforms. We've done a lot of work building this. I really ought to save this at this point in time. So I'm going to click here and do save as, and this will be WK-11.1 phase shift -1 by IMA sample. Well, you're going to type in your own name. Should name it. Okay, now it's named. That's nice. So now we're going to actually run this guy now. We want to leave this dialog box open. If for whatever reason it closes, like so, it's going to say, oh no, what happened? Here, the little gear symbol will bring it back. So touch the gear and it comes back nicely. All right, I do want to engage, we were in the schematic tab. We want to engage our split screen tab, split screen right there. Boom. We now have split screen, which is great. And we will be able to see what's happening on our waveform when we start running this circuit right here. So the play is right here. This is your go button, your play button. Boom. And while it's running, ooh, look at all those waveforms. Too many waveforms for us to look at and read, not a problem. We keep the dialog box open. We bring the scroll bar down. And by bringing the scroll bar down, you have the ability to play with time per division. I'm going to click here once, twice, one more time, 3 times. Now I've reduced the number of waveforms on my display. This is really nice. I'm going to hit pause. Pause. It's paused. I can reduce the number of peaks on here. I still have too many, so I'm going to do a run. And I'm going to click one more time here. That's good. And pause. Great. Now, the directions are on your sheet, peak of the voltage of the resistor using the horizontal cursor. Do I have a cursor tab right here on the right-hand side? It says cursors, yeah? I click on it, it opens up more. Click on it, it goes away. Click on it, opens up more. And I do want cursors, so I get to select the type of cursor. Do I want horizontal or do I want vertical? I want a horizontal cursor. Oops, sorry, the other way. Horizontal cursors is the y-axis. I have a C1, I have a C2. I don't need C2 for right now, but I want C1. And C1, my instructions were to measure the voltage of the resistor using the horizontal cursor. Well, my resistor is measured with what probe? The blue one, yeah? So my blue waveform is where I want to pull this cursor down and touch the tippy top of the blue waveform. And if I touch the tippy top of the blue waveform, just let it set there. Guess what? My cursor number 1, C1, the value's down here in this lower left-hand corner. What do you see? 7.6364 volts. And I'm going to write that down on my paper. 7.6364 volts. And you don't round that off. What did we calculate on our worksheet earlier? Didn't we calculate 7.57? Isn't that what we calculated on our paper earlier? This is pretty good. All right. Now, the next thing it asks you for is the time between the two waveforms. So to measure the time between the two waveforms, we have to change the cursor type from y-axis to x-axis. And here we will use both cursors. I can move the cursor number 1, okay, and I want to move the cursor number 1 as far as I can so that, if you will, focus your attention on the zero line and the blue waveform. The zero line and the blue waveform. Where the zero line right here and the blue waveform meet, I want to intersect that with my cursor number 1. Best as you can eyeball, move this back and forth gently, and best as you can, pin it as best as you can, just with your eyeball. Okay, and let's pin this one right there. Take your cursor number 2 and then move this over to where the green waveform crosses 0. And this one's a little easier because this one has a little dot that moves along. And you want that dot to sit right on that 0 line, right. It's a little above, just a touch, right. Come on, mouse, be nice to me. Right, I had it, oh darn. Right, yeah. Come on, there, that's close. I am measuring the time difference between the two waveforms. One waveform is, the blue waveform happens first, the green waveform happens next. They are clearly out of phase. By measuring the time difference between them, and how can I tell the time difference between them? Look at here, delta x. What is my delta x? 32.957 microseconds. Write that down on your answer sheet. 32.957 microseconds. That's on your answer sheet. Now the rest of this is academic. We've now gotten the information we want off of our multisim, and I'm going to go back to this paper. We recorded this from multisim as the peak voltage across the resistor. We recorded this as the time difference between the two waveforms. What is the period of one cycle? The period of one cycle, if you remember, was the time for one cycle. Well, what was my frequency? F is equal to 5100 hertz. So what is my T? Isn't T the reciprocal of F? Reciprocal of F, sorry. And so what do we do here? All you need to do is you take your calculator, 5100 by 100, and reciprocate that. And when you reciprocate 5100, boom, enter, engineering. Do I have the time for one cycle? 196.08, what's it say here? Microseconds. 196.08 microseconds. We're half a heartbeat away from getting done. You want to calculate the phase angle based on multisim. It is the time between the waveforms, which was 32.957 micro, divide by the period, 196.08 micro, times 360. Watch the magic. Now, you don't have to key in micro because the micros cancel. So all you have to do on your calculator is this, 32.957, and divide by 196.08, and then multiply by 360, or actually multiply by 360, equals engineering. What do we calculate on the calculator is the phase shift between the two waveforms, 60.51 degrees, and we'll call that negative. Does that compare reasonably well with your calculation up here using SOH CAH TOA? These two numbers are pretty good. So this is how we can use Pythagorean theorem, SOH CAH TOA with real-world electronic circuits and be able to verify our measurements and our predictions using multisim. And so with that, I thank you all very, very much. This should be able to get you going on this exercise. I promise that the deliverables list was completed, so it has been. All of your assignments are up in Canvas. Any questions for me? Okay, if no more questions, then I'm going to take my wonderful picture of all your smiling faces. We'll go to camera front. Yes. So wipe the dust off mine, and let's put this into gallery view so we can see everybody's smiling faces. Yes. And 1, 2, 3, smile. Cheese. Yay. Is this thing taking pictures? Yes, it is. All right. Have a lovely weekend. Thank you so much. Any questions that come up, by all means, catch me in Discord. Take care. Bye-bye now.